joining first, welcome everyone. And we are pushing live to LinkedIn and YouTube now. Okay, we are live on LinkedIn. I'm just going to check over here, make sure we're live on LinkedIn, live on YouTube. Wanted to double check we're live on LinkedIn. And as you're tuning in here, if you want to mention where you're tuning in from in the chat, say hello. Perfect. We are also live on LinkedIn. Excellent. Welcome, everyone, to today's community meetup for Delta Lake. I'm just going to share my screen here. Perfect. So, one moment here. Perfect. All right, everyone. Thank you for joining us today for the Delta Lake Community Meetup. We have a lot on the agenda. We have three panelists today. TD, a staff software engineer at Databricks, as well as Lars Kroll, another engineer over at Databricks. We also have Tyler Croy, a lead maintainer for Delta Rust, also speaking. On today's agenda, TD will cover Delta Lake on Spark 4.0. Lars is covering deletion vectors for update and merge commands. And Tyler Croy will be going over Delta Rust updates. If you have questions along the way, feel free to place any questions in your LinkedIn, YouTube, or Zoom chats. We will leave about 10 to 15 minutes at the end of today's session to go over those. I am also Carly Akerley, a communications manager over at the Linux Foundation. And with that, I am going to turn it over to TD.
Thank you very much, Carly. Okay, so today we're going to talk about the Delta Lakes more looking towards the future. In the last meetup, if you haven't seen, take a look. I spent a little bit of time talking about what happened in the Delta Lake community across various different sub-projects in Delta Lake in the last year. Now I'm going to talk about what is to expect in this year. One of the biggest event that is expected to happen this year is, whoops, I am not able to forward. Okay, no, it works. Okay. So one of the biggest event that is expected to happen is there's going to be a Spark 4.0 release. And this is a first major release, not the first, I think this is the major release after almost 4 years. So this major releases are often challenging. It brings in new features, but it can also has API compatibility breaks and stuff. So a lot of these new features gives new opportunities. And the Delta Lake project, we want to take advantage of those new features, new opportunities to make the users of Delta Lake give a better experience. So this will have a large impact on the Delta Lake roadmap. And as part of that, I'm going to do a brief look at 3 of the features that we are excited that we were currently working on and we're excited about, that it's going to make significant architectural changes in the Delta Lake, giving a lot more flexibility and better user experience. So the first one I'm going to talk about is Spark Connect. Spark Connect is a feature that is available since Spark 3.4. And it's a major architectural change in Spark itself. And to understand what the architecture is, let's look at what is one of the biggest challenge of using Spark that anybody who has used Spark has experienced. That your Spark application, the process in which you're running your Spark Java applications is basically running in the Spark's monolithic driver. So the same application is running your application code as well as all the heavy duty work that Sparks is doing to run the jobs on the Spark cluster and stuff. This close coupling between your application code and the Spark driver code leads to a whole lot of problems. So while you can access Spark from various different places in your own applications, IDE, notebooks, etc., even other programming languages like Python, R, it's not the most convenient to use and leads to all sorts of weird behavior. For example, since running your application code inside the Spark driver can cause a lot of instability. For example, if there is ooms that happens in your application code, it kills the entire Spark driver and the cluster together. So in environments where there are multiple users using the same cluster, it leads to one user affecting the running of the other user's code. So in multi-tenant environments, this is not great. Then upgrading your Spark application is challenging because you need to if the next version of Spark has lots of new goodies or has performance improvements that you want to use, you have to update not just the Spark cluster, but your application code as well to make it compile with the latest version of Spark. So it's so all application code needs to change or their builds have to change. Similarly, it is hard to work in an IDE to debug code interactively while connected to the Spark cluster, because there's some error that is happening only in the Spark cluster, not in when you're running Spark locally on your laptop. Then it's hard to connect to that and debug because there's just no way. So, and then similarly, no remote connectivity for any programming language code. Only for SQL, you can do JDBC, ODBC, there is Apache Livy, but that is restricted to only SQL. So we want to get rid of all these limitations. And so Spark Connect is a major way for achieving that. So what Spark Connect does is introduces a client API in the middle where the Spark driver becomes a separate process running as a server, and the application code is running in a separate process as a client. And all operations, as you do data frame operations, etc., they are generating Spark SQL logical plans, sending it over to the server to execute it. And then the server, which is the Spark driver controlling this entire Spark cluster, executes that logical plan and gives back the results to your client process via the same API interface. And so there's a clear isolation between your application code and the Spark driver. As a result, it solves all of these instability problems, etc., because of this tight coupling. Now to make this work, then basically all applications need to really understand how to work via the Spark Connect client API interface. So this is a major architectural change in Spark. And for some libraries that depend on Spark, like Delta, we also need to change Delta accordingly. And for example, Delta as a client-side library is not enough because Delta generates a lot of custom Delta-specific logical plans that the Spark natively will not understand. So there has to be a Delta server-side library that takes those plans that the Delta client library produces, understands them and how to execute them in the Spark driver, and sends back the result. So this is the architectural change for Delta as well when it's operating on Spark. And it needs changes in Spark 4.0 for this to work properly. And that's why this Delta support for Spark Connect is a feature that we are building towards to support Spark Connect. And for Delta developers, Delta users, there'll be more stability. Basically, your Delta app will not have to change as you upgrade Spark in the cluster, because as long as the client API is stable, you're good. Any version of your application will be able to work with any version of Spark server as long as the client API is respected by both the client side and server side. Similarly, better upgradability, better debuggability. Moving on to the next feature, type widening. This is a purely Delta feature, although it needs some changes in Spark to make it work properly on Delta's work, but is a feature. And to motivate this feature, let me paint a picture. It's one of the very common uses of Delta and Spark structured streaming, and that is that you are taking semi-structured data from various different streaming sources like Kafka with the JSON, with data encoded in JSON, and putting it and parsing it, doing ETL and putting it into structured form like Delta Lake tables. However, since it is semi-structured, the schema of this data is continuously can change. That's what the current world is. Schema of the data can evolve. And we recognize this challenge very early on in Delta, and we added this feature called automatic schema evolution early on in Delta Lake. Now, it has its limitations. To kind of understand that a little bit more, let's look at how can schemas change. One is new columns can get added. Like, for example, if you have products, new products getting new tags or attributes or additional features, those fields can appear, new fields can appear inside your JSON, and you want to capture those fields and add it to the Delta Lake table as well. And then similarly, the existing column types like can change. Like, for example, your order ID, products order ID. Earlier, it was a small number, it was int was sufficient. Then the order ID grows, it now needs a long. But your Delta table has already encoded it as int. How to deal with that? So these are the kind of changes that can happen. And we have to kind of be able to handle those. So for new columns, we've already solved the problem 3-4 years ago by adding automatic schema evolution. New columns are automatically added in the Delta table while doing an insert or a merge operations. It is an extremely popular feature, works with nested data, complex types, structs inside arrays, maps, etc. Over time, it has been built to be very, very, very powerful. But the challenge that hasn't been solved yet is changing column types. Like, you've already written out your previous data using int columns in the underlying Parquet data files. Now, if you want to start writing long columns, how do you resolve that? How do you do that without rewriting all the previous data that already has things encoded in int columns? So, and rewriting data is expensive. You need to halt your production level streaming job, rewrite everything, etc. It's messy. To make this easier, what now we are doing is we're building this thing is called type widening, which is the core idea is type reconciliation while reading. So Delta readers need to be upgraded to understand a new protocol where if it sees that column A has changed from int to long, then while reading all the data files, if it sees the data file has int in it, it will automatically cast it to long before providing Spark or the reader, the higher level, the user will do the automatic casting at the time of reading. So if old data, which has int, is updated to long, it will automatically update it to long while reading. New data, if it is already in long, then great, nothing needs to be changed. So this will allow a certain this reconciliation is possible to be done on the fly when for a certain specific set of data types. Like, for example, tiny int can be upgraded to small int to be upgraded to int, big int, without any kind of data loss and stuff like that. Similarly, decimal can be widened, float can convert double, date can be converted to timestamp, things like that. And to use this feature, we are still building it. It's not released, but Delta 3.2 will have a partial version of this as a preview. The bigger changes, the full version of it is going to come with Delta 4.0 because it needs Spark 4.0 changes. So enabling this is simple. You just enable this table property, and after that, you will be able to allow column types to be either manually or automatically upgraded as part of your insert operations and stuff. Moving on to my last feature I'm very excited to talk about. This thing is called managed commits. And to really understand this, let me walk through what the current world is. So stepping back, Delta as a format, as a protocol, is a completely self-describing file system-based format where the entire Delta log is on the file system and is this complete source of truth on how to read the rest of the Delta table, actually in the Delta table. So as your file system, Delta tables work with or without catalog. Basically, if you don't have a catalog, you can just write it to a directory and it's self-describing. You can read right from the directory. Great. If you have a catalog, the catalog, all it has to do is point to the directory and it works perfectly well. So the catalog just serves as a pointer from the nice table name to a location, a directory, and then the directory contains all the information that is needed. And to update the Delta log whenever there's a new change, then what we rely on is that the file system on which the data is residing on the provides some mechanism to create a new file only if it is absent. So put if absent. So, and the way it is used is that if there are two writers that are concurrently trying to modify the log, the table by creating a next version.json in the log directory, only one of the writers should succeed to create that object, because that object, that the next version.json doesn't exist. The other concurrent writers will temporarily fail and it will retry to create the next, let's say 003.json to commit its changes. So that's how a pure file system based table format works. And this works on pretty much all file system and object stores, modern object stores support it, except S3. S3 is the outlier. Now, to solve this problem, what we did is we added this feature called DynamoDB log store, where the DynamoDB is used as a coordinator or a manager for commits. So instead of doing a conditional put if absent write into S3, we do a conditional write to DynamoDB to define version 2 has these changes. So what is version 2? And so once it is committed in DynamoDB, then we sync to the file system to make sure version 2 is also synced to the file system and the file system is self-sufficient, self-describing once again. This works absolutely great. The only limitation is that the users have to configure this to make sure that you don't write to S3 file system directly, you write via DynamoDB and stuff. And it's not a solution that is very generalizable and extensible to other kinds of coordinators that one may need to use. That's where managed commit comes in, where we are defining something, a commit manager in the protocol itself. So the log of a table itself defines that who is allowed to commit to this log. So here, if the log says that I am managed by DynamoDB, this particular DynamoDB table, then writers following that protocol have to go through DynamoDB, conditional writes on DynamoDB to update the log. And writers that follow the protocol but are not correctly configured to work with DynamoDB cannot update and write to that log. So it is correct and enforced out of the box, much safer. That's benefit one. Benefit two is that now it is extensible to any system. Like instead of DynamoDB, you can say that, oh, a different catalog, let's say Hive Metastore, is actually the coordinator. So you have to always conditional write in Hive Metastore before to update this particular table or some other catalog. And that's the second benefit. And the natural extension of that is that in your application that is combining data from various different sources, coordinated by different catalogs, etc., you can update tables from your application across various different things. That adds a huge amount of flexibility to the applications you can write while ensuring end-to-end correctness, etc. So Now, there'll be more details coming on this. There are GitHub issues on Delta. You can start looking at it for more details. But wrapping up, so with Spark 4.0, there's a lot of architectural changes expected. Also, some breaking changes, backward incompatible changes expected because major release based on semantic versioning allow backward incompatible changes. So one proposal that we are floating right now to the community is that the first version of Delta on Spark 4.0 will be Delta 4.0 as well, so that we can accommodate those potentially breaking as well as large architectural changes. Now, the Spark 4.0 is not, the timeline of that is not clear yet. So we're going to continue releasing Delta 3.x on Spark 3.5, which is the last release of Spark on Spark 3x. So we're going to continue releasing that. The next release is Delta 3.2, which is expected to be early March. But this idea was very well received by the community. We post such ideas in the Slack channel, and this proposal was very well received. So more news to come. So stay tuned on the Slack channel. Join the Slack channel if you're not already in it and stuff. That's it from my side.
Awesome. Thank you so much, Chidi. And we will pass things over to Lars now. Lars, you have screen control.
Oh, thank you very much. All right, so I'm going to talk about deletion vectors and in particular the recently added support for the update and merge commands. And I'm going to do this in 4 steps. The first 2 are essentially giving some background so that everyone can follow along no matter how much time you've spent looking into this before. And that is essentially recapping what are deletion vectors at all. And secondly, some background on how update and merge commands work if you're not using DVs. So they worked until we introduced this support. And once we have covered that, then we'll go into detail on how can we actually use deletion vectors to improve update and merge. And once we do that, what do we gain in terms of performance? Okay, so what again are deletion vectors? Well, looking at it from a very high level, it's essentially a mechanism to track rows that have been logically deleted, but they are still physically present in a Parquet file that we currently consider part of the live data set. All right, so let me give you an example kind of how we get there. And I'm going to use delete as the command because it's very obvious to see for a delete command how you would apply deletion vectors. Okay, so let's say you want to delete all the rows from the Parquet file on the right. So that has 2 columns, X, Y. And I also kind of wrote out the actual row index as if it were a real column, but of course that isn't materialized in the file. Right? We can infer that from where the rows are, but I just wrote it out for clarity here. Okay, so let's say we want to delete all the rows where X is either 103 or 105. Okay, so those are the rows with index 1, with index 3, and index 4. Okay, so without deletion vectors, how this would proceed is we basically completely ignore the rows that we want to delete, and we just take all the rows that are left after the deletion and rewrite them into a new file. Okay, so then we basically get a file with 2 rows, the ones that are not 103 or 105 in column X. Okay, and every time we do this to a file, we basically copy the remaining rows. With deletion vectors, instead, we will do the following. We basically write a much smaller file that only contains the indexes of the rows that we deleted, and we call this a deletion vector file. Now, that means that when we go and read the data then at the snapshot that where the DV is valid, essentially, we have to recombine this. We have to reconcile this view somehow. Right? And the way we do that is that basically during read, we subtract the rows that are in the deletion vector from all the rows that we read from the Parquet file. So we read the entire Parquet file, and then we filter out all the rows where the index is currently in the deletion vector file, and we return whatever is left, right? That's equivalent to copying what was left, what we did before. But of course, the nice thing about doing it this way is that we don't have to copy the remaining rows every single time we do a delete. Instead, we can do this a couple of times. Let's say, we do another round, we delete the row with x102, so that's the 0th index. We create a new DV. We don't create a new file, we just create a new DV that has all 4 row indexes 0, 1, 3, 4 in it. And then the logical view is just the row with 104. And at this point we go, okay, look, we've deleted, was that 80% of the file? Maybe it's a good time to compact this out, right? So at this point, we go and we do what we would have done before. We rewrite the remaining rows into a new file. Maybe we compact it with some other file. And what this process has gained us is essentially that we have some time to amortize the rewrite cost of remaining rows over multiple delete operations, right? This could be a couple of 100 delete operations before so much of the file has been deleted that we go, okay, maybe it's good to compact this out and get rid of all the dead rows. Okay, you can pick some threshold there that corresponds to how much you're willing to pay for it, basically. Okay, so that is how deletion vectors work at a very high level. Okay, so how did update and merge work again before we introduced deletion vectors? In many ways, quite similar to how delete work, right? So we still have, let's say, an update, right? Let's say we have some kind of row selection mechanism, just like we had before. It's some kind of predicate that tells us which rows we're going to touch and which rows we are not going to touch. And what we do is basically we specify what we want to do with the rows that we touch. Let's say we want to update column Y to always be U in the rows that we selected, that match the predicate, right? So that's the yellow rows in this file. And then what delete simply does is it copies the entire file, and while it is copying it, it basically takes the rows that we didn't touch unchanged, and the rows that we did touch, it changes the columns that we told it to change to the new value. Okay, so it looks basically like this. Okay, that's how update works. Quite straightforward. Merge is a bunch more complicated, but at a very high level, it kind of does the same thing. So we still have some kind of mechanism to select rows, and there are 2 variants now. So we can either select rows that match with the source plus match some extra condition, or the rows that do not match the source plus some extra condition, all right? And all the rows that we didn't select, they still get copied, just as before an update and in delete. Okay, and then, in merge, you can also have like different actions for the rows that you selected or that you didn't select. They can be update or delete. That's not really the important part right now, what you do with them, but and also you can insert rows. Again, this isn't really relevant for a DV discussion. It doesn't matter if you insert some rows on top. That doesn't change what we do with the DVs, okay? So let's take the example here, same file as before. Let's say we have this merge statement, which very quickly summarized basically takes all the rows where x is 103 and updates them such that y is u, and takes the row where x is 105 and just deletes it. Okay, that's the summary of this merge statement. Okay, so if we execute this without deletion vectors, what we basically do is we rewrite unchanged the rows 0 and 2. Those were the rows that we didn't select. And then we update the rows 1 and 4. Those were the ones that were matched by the 103 value of x. And we just skip the old row 3 because that one had 105. We deleted that one. Okay, that's how merge works at a very high level without deletion vectors. Okay, so now that we've kind of looked at this, we got to think, so how do these actually help us in update and merge? Like at a very quick glance, merge does do a lot more than just deleting rows, and update doesn't even delete rows at all. It just rewrites everything, right? So how does it help? Well, does it not delete any rows? Let's look at the same thing from a slightly different angle. what they really do, if you kind of zoom out even further, is we actually delete all the rows in every touched file. And then we reinsert some new rows that correspond to the following variants. Either there are updated and inserted rows in terms of merge, or they are copied rows that we didn't select before. And for those copied rows, like what we logically did is we deleted them and then we reinserted absolutely identical rows again into the data set. Okay, and this is actually the part where deletion vectors can help us, because both commands actually copy unselected rows in this delete and insert manner from a very high level, right? Exactly like what delete does. So what we can do is we can apply deletion vectors to those rows. Okay, so how does this work? Let's say we want to do an update with deletion vectors, okay? So we have our predicate, we select all the rows in 103 and x 105, just like before, same example. And then what we do is we take the rows that need updating, so that's rows 1, 3, and 4, and we write those rows into a new file with the updated column values, just those rows. We do not touch the rows that weren't selected. That's rows 0 and 2. And then, in addition to writing this new Parquet file, we also write a deletion vector file. And we use that to mark the rows that now should not be read from file 1 anymore, right? Just like in the delete case, we mark the rows that we deleted. Now we mark the rows that we updated because they exist with their new values in a different file now. So we shouldn't read them twice from 2 files, okay? But we leave rows 0 and 2 untouched in file 1. And then when we read both file 1 and file 1 new Parquet. It's just file 1 we read together with the DV, right? With the DV applied in the same manner that I described before by subtracting the rows on read. Okay, and then the union of those two basically gives you the correct result. When we do merge, we do essentially the same idea, right? So let's say we have the same merge command as before. We selected rows 1 and 4 for update, and row 3 is now a delete. Right? Again, in the same manner, we produce a new Parquet file by rewriting the updated rows. So rows 1 and 4 go with a new Y value into file 1 new Parquet, basically, the new file that we wrote. And if inserts happen, we also throw those in there. They go together. And then the rows that were deleted, we don't rewrite them at all. And all the rows that we selected, so that's the updated rows and the deleted rows, they go into a deletion vector, right? Rows 1, 3, and 4. And then just like with update and delete, when we read file 1 Parquet together with the deletion vector that we wrote to eliminate the rows that have been invalidated, basically, the updated and deleted rows. And we union that with file 1 new Parquet, which contains the updated values for the rows. Okay. All right. That is the idea for both merge and update. Quite similar, really. Okay, so what does this give us performance-wise? Well, as always, results depend somewhat on your workload, but suffice to say that it can be very, very good, right? If your workload was previously heavily bound on rewriting all of those redundant rows, which, writes take a lot of time, then you can get massive performance improvements. So we have this experiment. It's a relatively small table, 3 GB table, 20 columns, just completely random data, basically. And if you delete a tiny number of rows, right, you get about a 10x-ish performance improvement over rewriting all of those unchanged rows. And of course, as you would expect, as you increase the number of rows that you're eliminating, the benefit gets less and less, right? Because, well, the other one has to do less work now copying rows, essentially. Okay. For merge, slightly bigger experiment, 100 GB table, only 4 columns. And let's say, right, so you can also see as we increase the number of rows that we are eliminating via deletion vectors, So this is the merge that actually just does a delete, but it's still done via a merge. You can see that the performance of without DVs and with DVs kind of gets similar, but still at small deletion percentages, you get a very good performance improvement. This is about 3x, 3.5-ish x at the 10 to the power of 4 rows level here. All right, and then, you know, eventually you come to more or less the same performances without DVs as you delete more and more. So what do we pay, right? Things are generally not for free. And I said it's an amortization thing, so there's usually some kind of trade-off we're making with this amortization. Okay, so let's look at the post-merge read performance for exactly the same experiment that I just showed you for the merge. You can see that for all of these deletion sizes, the impact is, I would call it hardly noticeable, right? So even at 10 to the power of 7, it is a very, very minor read regression compared to the non-DV case. If you keep doing this, eventually you will see some overhead, right? So once you go to like 50% deleted, you will see not a 50% overhead, but you will see some overhead, mostly because you read redundant data, right? If you have 50% of your file deleted, you read basically twice as much data as you need to. So that is some overhead. So that's why I said you probably should set some kind of sensible threshold for this at which you compact things out to not have so much overread. But just turning DVs on, there's essentially no overhead for having like a very, very small number of rows deleted just from the application of the deletion vectors. So from that perspective, it's almost for free. All right, that was all I had.
Awesome. Thank you so much, Lars. We will turn things over to Tyler Croy now. Thank you.
Hello. I wish I could say that deletion vectors were now available in the Delta Lake Rust or the Delta Lake Python packages, but they are not. I wanted to share a bunch of the latest updates and sort of where we are, where we're going with the, colloquially we refer to it as the Delta RS project, but it's really the Python and Rust bindings for Delta Lake. And we've got 0.16, which Eon and a number of other folks have helped push out the door. And we've got initial schema evolution support. We've had a lot of performance improvements, faster merges, drop constraints, and then time zone support, or timestamp with time zone support. That represents, that last one is something that I think is interesting to call out if you've not spent a lot of time working between like Spark, the Databricks runtime, Apache, Parquet, Rust implementations. Like time is sort of a wacky, not everybody's consistent about what a timestamp should look like or what it will or will not have. And so we still have some ongoing work that we need to do in supporting various flavors of timestamps in the Delta Lake or Delta RS project. And so if you have really interesting data or really old Parquet data, or Parquet data that's worked with from multiple systems, it would be really interesting for you to help us test some of that time zone support with timestamps, because it is sort of an interesting area of development. One of the things that's interesting about the Python packages is we sort of put all the batteries included, very Pythonic in that way. And so the latest 0.16 releases kind of have unreleased Rust changes as well. So that's where some of that schema evolution support came in. They also have newer versions, or typically will have newer versions of Data Fusion or Arrow and the performance improvements that come from some of those underlying dependencies when we cut those releases. There we go. Remote controlling. With Rust, we cut 0.17 in February, I think. So if you do a cargo add of Delta Lake, you'll get 0.17. This is a big release. I can't understate how big of a release this was, especially for AWS users of the Rust crate. We threw out our DynamoDB lock implementation, and we adopted what we refer to as the S3 DynamoDB log store implementation. The key difference between those two is the DynamoDB lock was a Delta Rust specific I'll call it a protocol for concurrent writes on AWS S3. S3 DynamoDB log store is a shared concept, a shared protocol, shared algorithm, I'll say, that Delta Spark uses and now Rust uses. So the Python implementation also incorporates this. And so we have some tests that exist, and we have users that are adopting this, where they will have, a Delta Lake Python Lambda or a Delta Lake Rust Lambda doing appends to a table, and then Delta Spark coming along and doing big merge operations or big queries or big compactions or optimizations and things like that. And those will coordinate just fine together, which is really exciting. So that S3 DynamoDB log store support is now, TD's like, woo! In the background there. Very happy. We've made TD very, very happy with that support. But that means that we now have an ecosystem around AWS S3 that will allow a lot of portability between different writers for what Spark does really well, what Rust with Lambda does really well, or what Python with pandas or polars does really well, which is really exciting. We also have that same initial schema evolution support that comes in the Rust crate, that comes through the record batch writer. We have a couple of different writers. We've got a writer implementations in the Delta Rust code, which we have to rectify a little bit over the next release or two, sort of consolidate so that everybody is having the same schema evolution support, the same fundamental, table operations. But one of the things about that schema evolution support that is not supported, that I wanted to call out, is schema evolution within structs, or it's just on columns. So if a new column shows up, then the schema will get evolved to include a nullable column in that represents that new data that comes along. But if the type binding stuff that TD was mentioning earlier, we don't have that yet. Schema evolution within a struct has new submembers within it. We can't do that yet. 0.17 is also really exciting for me personally, because I did a lot of this painful work. We now ship multiple crates, and so you can continue to consume the Delta Lake crate, which is sort of the meta package that has features like the Data Fusion feature, the AWS, the S3 feature, the GCS, and the Azure feature. Or you can just pull some of these sub crates. Like if you just need the sort of protocol level stuff, you can just pull Delta Lake Core, and that's the dependency. Or you can pull Delta Lake Core and Delta Lake AWS as packages. And in order to do that, we had to allow for extendable storage support. So any other storage provider can produce a Delta Lake crate that can plug in their storage provider. They basically register their URL scheme, and then Delta Lake Core will delegate to their implementation of an object store trait, basically. This opens up a lot more extensibility without requiring everything to come through the Delta RS sort of release train. So Delta Lake AWS, as an example, can and is being released independently. And so we're going to be following semantic versioning as we push towards 1.0 for the Delta Rust project, which is a good segue to what is coming up next. We have some pull requests open already to improve schema evolution. Very popular feature. I'm surprised how popular that is. We also have some initial work that was started by one of our contributors, Stephen, on change data feed support, or CDC if you go look at the protocol. We're looking at that both from a reader and a writer standpoint. And what's exciting about that for readers is you can just see just give me the data that's changed. And what's useful about that for writers is obviously as you have these multiple Spark and Python and Rust implementations, everybody being able to emit change data feed files. I don't know what I would refer to, but emit those changes also allows it brings the whole ecosystem up in terms of writing Delta with Delta RS and Python. We also have some Data Fusion Arrow updates. Those are sort of perfunctory. There's always improvements from the Apache Arrow project and the Data Fusion folks that we love to pull in. And we also have a number of performance improvements that are coming. In 0.16.0 of the Python package, we improved releasing of the global interpreter lock. And there's some more improvements to allow for better concurrency and higher throughput on the Python side that are in progress right now. I should say also, if you go look at the discussions on the Delta RS project, there's a discussion that I started to discuss what we want in 1.0 for Delta RS. And 1.0, because we believe, or we want to follow semantic versioning, that's where we will be locking APIs in to that major version. And so the APIs will then remain stable for a period of time. Who knows how long, but for a period of time as we iterate. And so I'd appreciate feedback on what should or should not be in a Delta RS 1.0. We also have really new fancy language bindings, which is really exciting. So a contributor named Kaija, he started working on .NET bindings built on top of Delta RS. That's already available in the Delta incubator under delta.net. If you are interested in pulling Delta Lake data into a .NET runtime of some form, regardless of your operating system, go check that project out. Kaija's been working on it. I think we could use more people that really know .NET to make that successful. And literally yesterday, one of the sporadic contributors to Delta RS proposed some node bindings, which is really exciting to see. One of the reasons that we originally invested in Rust is because Rust is very portable and embeddable to these other languages. And so we're working on figuring out where that Node.js code is going to go, but hopefully that allows us to pull Delta data into Node or other V8-based JavaScript runtimes, which is very exciting. The project, Delta RS in general, needs more people. We always need more people. We love to, love to party. We'd love you to join us in the party. I would say most acutely, Matthew Powers and a few other folks have been doing really good work on our documentation. The Delta RS doc site reflects that. We need a lot more help on the Rust side, I'd say, more than the Python side. Adding examples, writing out a narrative version of, here's how you use Delta Lake and Rust. We also need more feedback. 0.17 from a Rust standpoint was a big release. So more people adopting 0.17, letting us know how it goes, positive or negative. Hopefully it's positive, but I'd love to have positive signal as well. You can join us in Slack, or if you've got a problem, just report it on GitHub. And if you're feeling like a quality bend, adding more unit or integration tests that represent your use cases in Python or Rust is a really great way to ensure that subsequent releases of Delta RS for Rust and Python properly support the way in which you are using or interacting with Delta Lake. That's it. I tried to do a speed run as quick as I could because everybody's got stuff to do. So thank you very much. Back to you, Carly.
Awesome. Thank you so much for that. So many exciting things happening in the Rust community. So it's awesome to see. With the last about 12 minutes here, we do have a few questions coming in from the audience. If you have any additional, feel free to place it in the chat. We'll get to it shortly. So first off, Ravi in Zoom asked, how can we handle OMM and GC overhead issues?
That feels like a TD and Lars question, because when you use Rust, you don't have any GC.
Yes.
You do in Python, but I'm assuming that he's referring to a JVM-based implementation.
Yeah, I'm guessing so. So OMM, I'm guessing that means OOM, which out of memory error and GC overhead issues. Yeah, there is no magic bullet to that. It's like any Java application. You have to be conscious about what code you're writing. I mean, for example, there are basic guidelines that are no-brainers especially when using Spark. For example, one thing I can think of is do not use dataframe.collect or rdd.collect if the amount of data you're collecting is expected to be very large. So think twice before using rdd.collect or dataframe.collect, because it will collect your entire distributed data set into your driver's memory. So you got to be conscious about the impact of each operations and stuff. So that is just Spark knowledge.
So
Spark.
TD, like what is a no-brainer or simple for you is still like way above my knowledge of anything Spark. So I know like one of the things that I really like about Delta as a format is there's file stats and there's information in the Delta log itself on like how big data is. And so I know that you can get like the table size with described detail. How would I know if I've got a data frame that it's too big to collect, or that I'm like the data set that I'm working with is going to exceed the amount of memory on my machine? Or on a driver or worker?
Yeah, good question. Yeah, I agree. Like when I said no-brainer, I was thinking about general Java stuff. But yes, this Spark thing, it takes a bit of knowledge and art and experience. And you're absolutely right. For a general data frame that you have computed based on some table or something, it's hard to know whether it's going to be small or large. So advice that I've given in the past is to think in terms of production code versus testing code. Like before running something in production where is or GC overheads or slowdown because GC is really bad, go through this testing process, staging process and stuff to see whether the data that you're collecting in your production ready code is large or not. So that's a general principle to before you run in production, test it out heavily. But in terms of other things for data frames, if you don't know ahead of time that in production whether you will get whether the data would be large or small, you can program defensively, like things like instead of doing dataframe.collect, do a dataframe.count and see if it is large. If it is large, then do something else other than dataframe.collect. If it is small, then go ahead and do it. So these kind of defensive programming, it makes things a lot more stable in production.
Excellent. Thank you very much, TD. We have a question here for Lars. When we do merge with deletion vectors, will compact operations still happen occasionally?
It will not happen automatically. The expectation is that tables that are used with deletion vectors schedule a regular optimize, and optimize will take care to keep the number of deleted rows or other percentage of deleted rows at a level that gives you good read performance, basically.
Yeah. Let me add to that a little bit. So independent of DVs, at a table, even if you didn't have DVs, but you're merging heavily, there is potentially a lot of fragmentation file rewrite happening. So it's natural that you should be running optimize on a regular basis. So with DVs, this doesn't really change. You should still be running optimize anyways, and optimize will take care of this. Now, in Delta 3.1, we also released a feature called auto compaction, which makes it easier to delay the optimize to a much less regularity by running a kind of a mini compaction job after every data operation. So this is all Delta Spark. So this auto compaction, as of now, as far as I know, is not DV aware, but that is something that is worth improving. For example, someone can contribute. It's an idea that right now the auto compaction looks at, okay, what are the files that are small? And then do a mini compaction on them after any write operation. But it can be made more intelligent where it not just looks at the file size, but looks at the DV, what fraction of the file is deleted, and be smarter. So these are improvements that can be made to get better out-of-the-box performance that we are working towards continuously.
Excellent. Awesome. Another question here from YouTube. What if the source data changed in reverse? Meaning from long to int, will this be allowed since we can still upcast in the int to long on subsequent reads?
I believe this is already allowed. as far as I'm aware. I think at least with Delta on Spark, it will already automatically upcast if it receives an int and expects a long.
Yeah, I think the insert operation or a data frame write will automatically allow writing a data frame which has int in it into a table which expects a long. It will automatically upcast it. So this just nothing needs to change in the table to allow that to happen. It's perfectly fine to write int data when a table has a long column.
Awesome. Another question, how will Delta tables identify the records that were there in previous runs but now stopped coming in new files?
I'm not 100% sure how to interpret this question. I think what is meant is the rows that previously were copied unchanged into new files and that are now instead left in the old files and marked those that you still read when you read it with a deletion vector. That's my interpretation of this question. I was correct. So the way that this is identified, I mean, nothing identifies this rows in particular, right? They are basically existing in data, so they don't need to show up in CDF or anything. But the way that they are found again, so that they're included in the read set, is basically that the old file gets annotated in the delta log with the deletion vector, right? And then when you read it, it just looks like, okay, it just looks like any other file. It's just like, it says this one, read it with the deletion vector, so that those rows will end up still being included. So it just looks like a live file, just with an extra annotation of, okay, you should be ignoring some of the rows in here, but those other ones are still there. I hope that answers the question. That's how I understood the question, at least.
Excellent. Perfect. This question came in a little earlier. I think it was already partially addressed. Are deletion vectors live in Delta Spark? And the second part of that is, how do we enable or disable deletion vectors in Spark?
Yes, they are live in Delta Spark. You enable them with a... Sorry, TD?
We should clarify what live means. It is supported, but in Delta, as of Delta 3.1, it's not enabled by default.
Yes, that's true. Which gets us to the second part. You can enable them on your table by setting the table property delta deletion vectors enabled equals true, and will automatically upgrade the protocol of the table to be deletion vector aware. It is a protocol update, so it's going to be incompatible with connectors that cannot read deletion vectors. And it will start using deletion vectors as long as this table property is set to true.
If you go to the Delta,
I want to highlight that deletion vectors and change data feed support or CDC support. Those both will update the minimum reader and writer version. So if you have Python or Rust code floating around, be very careful. I have seen people upgrade tables and basically make that underlying change to their data that makes them incompatible with Python or Rust. So if you have Spark and Python floating around, or Spark and Rust floating around, I would encourage you to hold off on enabling deletion vectors, regardless of those wonderful performance numbers that Lars showed, because you will then lose the ability for your Rust or Python code to interact effectively with that table. We do have work to fix that for both deletion vectors and CDC support. Those are two of the big things that I had listed in my desired list for Delta Rust 1.0.
Yep. Very popular features.
Awesome. Thank you to our amazing panel and the awesome audience for the great questions today. We covered a lot of things, but the conversation does not need to stop. Join us on Slack, LinkedIn, X. You can check out the Delta Lake roadmap as well. We also just recently released the Delta Lake State of the Project if you want to catch up on what we've been up to the last few months. Thank you all again. And with that, we will end today's Delta Lake Community Meetup. Thank you.
Thank you.